Hello, my name is Dendon. In this video, I'm going to show you how to derive partial trace x inverse with respect to x. It's negative x inverse squared. Okay. X is n by n matrix. We assume. So the takeaways in this video include the definition of trace function first, and the derivative of an inverse function. We're going to find out what is that. And also the derivative of a trace function is the trace of the derivative. And lastly, we're going to derive the derivative of scalar by matrix. So first, let's take a look at the trace function of a matrix. So we assume that X is n by n matrix, and Xij represent the element at the ith row and the jth column in X. So the trace of X is equal to this summation of all the diagonal matrices. Okay, not diagonal elements. Okay, so basically you sum the diagonal elements in X together. So say you have this matrix X 1 1 and this diagonal element X 2 2 and all the way to X and N. Okay, and the rest we don't care much. X1 2 to X1 N, and this is X all the way to N1. Okay, so we sum the diagonal elements together. Okay, and that will be the trace. So the trace actually you sum all the elements in the diagonal of the matrix X is a number, so we call it a scalar. So the trace function is a scalar function. And now one important property of the trace function is if you take a trace of a matrix A times H is B, that's equal to the trace of B times A. Okay, so why is that? Let's take a look at this. So we start from the A times B. Okay, so if we look at the ij element of the product of matrix A multi multiplied by matrix B ij. Okay, so that element is computed by the ith row of A, that product to the jth column of B. Okay, so if you write it down, that's gonna be the summation. Okay, with a k goes from 1 to n. Okay, the aik times bkj. That's the ith element. That's the ith row and jth columns element of A times B. Okay, so the trace of AB, okay, is therefore if you let ij equal to each other, and we use m for example. So we say summation. Okay, m goes from 1 to n. Okay, and then summation k goes from 1 to n, and then you let I equal to j, so and equal to m, so it's a m k times b k m, and that will be the trace of a times b. Okay, and now we can because this element times element, and we can swap them. Okay, so it becomes summation, this is m. Okay, just use m, and summation k. Okay, so write down, and then we swap these two terms. So you put b together, b not put b put B first, BKM, and then AMK. I just copy it over, okay? And now the summation M and K can swap because you basically iterate over each. So you can swap K and M. Okay, so it's summation K, summation M. Okay, and then this is B, KM, and AMK. Okay, and you can see that this dummy variable KM, so M is here. Okay, so this is very similar to when we do A times B, right? A times B this. Okay, so this is actually we sum the diagonal elements when we do the B multiplied by A. So it's actually equal to trace BA. Okay, so you actually swap the order BA and AB, and the trace will remain the same. Okay, so we do one step further. If we have A times B times C, for example. Okay, so here trace A times B times C. Okay, and you can look at these two first. This A times B, let's say that this be the M matrix. Okay, so that'll be equal to trace. Okay, M C. Okay, and based on this trace AB equal to trace BA, so trace MC is equal to trace CM. Okay, and trace CM, if you put M back, it's gonna be trace CAB. Okay, so trace ABC is equal to trace C if you move C to the front, CAB. Okay, and you can do it one more time. Move B to the front, so it equal to trace BCA. Okay, so basically it's rotate the trace. Once you have trace of the three matrices multiplied together, so you can rotate the real one to the front, and that remain the same. So this is a good property of the trace. So now next we're going to study the derivative of an inverse matrix. So let's assume we have the A matrix and B matrix, and they are all the function of x. That means all the elements in A and also in B is a function of x. X is a variable. Okay, and we also assume A inverse exists. Okay, and we want to find out what is the inverse derivative of A. What is the A inverse? The partial A inverse with respect to x. Okay, so to figure this out, first we need to start out the matrix version of the derivative of product. So remember, if we have for example, the two function f1, f2, okay, and we want to find the derivative of f1 times f2, so it's equal to f1 derivative f2 times f2 plus f1 and f2 derivative, and this is scalar function version of the product derivative rule. Now we're going to find out a b. Okay, so let's say a b uh, it a b matrix. Okay, they are all function of x, so we want to find out partial a b partial x. Okay, and here the partial a with respect to partial x is a variable, is defined as matrix like partial, okay, A element 1 1 partial x, okay, and partial A12 partial x all the way to partial A1n, I don't know the space here, partial x, and then all the way down to the n1 partial x, and the last one is partial ann partial x. So that's a matrix. Okay, and that's the definition. And this is a numerator, and both numerator layout and the denominator layout. I'll talk about that later. Okay. So so what is the partial a times b with respect to x? Okay. So we we try to find this the ij element of this. Okay. So the ij element of this is actually the product, right? The product of AB at the ith row and jth column. So we see the product earlier, right? So that's summation. Okay. A I k times B k j. Okay. That's ij's element. And summation k goes from 1 to n. And then you partial this with respect to partial x. And that is the ij element of the product. Okay. And since this is summation k goes from 1 to n, this is two function times together aik times bjk. So the partial derivative can go inside and we still do the same. So it's summation partial aik times bkj with respect to partial x. Okay, and we have the aik times bik. So this is equal to summation a derivative. So it's partial aik with respect to partial x times bkj and plus aik times partial bkj with respect to partial x. Okay, and again we are summing k. Okay, so now we have two terms, this term and this term. So you can split them out. So that will be equal to summation k, okay, partial a I k partial x times b kj plus summation k, and then this is aik times partial bkj with respect to partial x. Okay, and notice that this is kj's term of it. Okay, so this term, if I transfer back to the matrix notation, okay, this is like the partial a with respect to partial x times b. Okay, and this term is a times partial b with respect to partial x. So altogether we have this partial a times b with respect to partial x is equal to a derivative times b plus a times b derivatives. So this is the matrix version of product rule. Okay. So once we have that, okay, so we are going to, what are we going to do? We are going to find the partial A inverse, right, to x. So we start out the A inverse times A is I, right, the identity matrix. So we do the partial this guy to partial x should be the partial identity the constant with partial x. So for the constant, the partial is 0. Okay. And for the partial A inverse times A, okay, we can use the product rule. So the partial A inverse, okay, with respect to partial x times A plus A inverse times the partial A to partial x. Okay, and this is equal to 0. So now, because A inverse exists, so we can times all the terms with A inverse and move this term to the right hand side. Okay, so that we will leave out this term. Okay, so that if we times A inverse, so this will be I, and there's another A inverse right here. And move this side, move this term to the right, it becomes negatives. So we have partial A inverse to partial x, it become negative A inverse, and partial A to partial x times another A inverse here, A inverse. Okay, so that will be the derivative of inverse function with respect to x. So now we got that, and let's move on to the derivative of a trace function is the trace of the derivative. So what that means is we have this, the derivative of the partial trace A with respect to x is trace partial A to partial x. So this is straightforward. Okay, so we start off from the partial trace A. So partial trace A is equal to partial. We know trace A is a summation. Summation A. Let's say summation M A M M. Right. All the elements together. Okay. That's trace A. And with respect to partial X. Okay. So this is equal to summation. Okay. Summation of partial A M M with respect to X. Okay. And so since we only sum the diagonal terms of this, okay, and we can expand that to just we can expand you can expand this, okay, to just part to the all elements of A to partial X, okay, because we sum the diagonal only, so we do not care about other partials with respect to the x, with respect to x. So the partial A to partial x, if you expand it out, is partial A11 to partial x, partial A12 to x, all the way to partial A1n x, and all the way to partial AN1 x, partial x, yes, partial x, sorry, and all the way to partial ANN to partial x. Okay, and so we only sum the diagonal together. So this can be just this. We can put it in. And when we sum all them together, okay, for the m, and then partial a to partial x, we put it in. And so we can put this as mm, just as the diagonal term. And this is essentially the trace. So this is a trace. So this is a trace of partial a to partial x. So that means in the partial can go inside, okay, So partial trace is a trace partial. Okay. So we figure this part out and move on to the next one. Now, derivative of a scalar by matrix. Okay. So that means we have a scalar function and with respect to a matrix X. So let's say we have f is a function over a matrix X n by n. Okay. Then partial f with respect to X matrix is defined as partial f with respect to partial x11, the first element, and then the this one is partial x n1, not 1n, okay, n1, and this is x1n right here. So you have a matrix n by n this way, and organized this way is called the numerator layout, also called Jacobian formulation. And obviously you can transpose that. You can have another way. You can put one n to here, right? And that's another layout. Okay, you can do that. So it's based on the denominator x, and we call the denominator layout, and you also call the Hessian formulation. So in the follow derivation, we'll use the numerator layout, and notice that this two is actually just the transpose for one another. So the partial f to partial x. Okay, let's say if this is a Jacobian, the numerator layout, and that will be the transpose of the Hessian layout, partial x. So they say this is a Hessian layout. So this is just a transpose. Okay, so these two are transposed from each other. Okay, because the definition is different, and we use the numerator layout, the Jacobian formulation in the following derivation, but the answer can be just transposed, to be another. So let's get to the point that the transpose x inverse. Okay, transpose x inverse with respect to x. Okay, and then we'll put a trace here. So the trace x inverse, this is a scalar function. Okay, with respect to x, scalar function with respect to x. So we have we want to show that it's equal to x inverse square, or x inverse times x inverse. So we first start from here, the partial transpose x inverse with respect to ij. We want to find the ij's derivative. Okay, first. Okay, so now if we do that, then this partial transpose is equal to transpose partial, so it's a transpose partial x inverse to partial xij. Okay, then this also equal to because this is x inverse with xij, right? So it's equal to we just derive the inverse derivative. It's negative x inverse, okay, times partial x with respect to partial xij, and times x inverse from the previous derivation of inverse derivative. Okay, so now we let the b a matrix is equal to this one, because the x is n by n, x is n by n matrix. S inverse also n by n matrix. So the n by n matrix times another n by n matrix, which is b, we let it to be times x or inverse also, or n by n matrix, and with that b equal to the middle part. So b is actually partial x with respect to partial xij. Okay, and we know that this matrix is all zeros except that the index would be lk, the index l equal to I and k equal to j is 1, because by definition, okay, by definition of the partial x to partial xij. So this B matrix, it looked like something like, let me show you. So this B matrix like this, okay, like this. The ith row, okay, and jth column, because it's a partial derivative of the element with the xij, so this is 1. And the rest of it nothing to do with the xij, so they are all zeros. So everywhere is 0, 0. So only here is 1. So ith row and jth column, ith row jth column is 1, the rest of all zeros. That's the B. Okay. So now we have the transpose x inverse. Okay, now equal to this guy, this guy, this guy. Okay, and now we just look at the i's j's element of it. Okay, so if you do the multiplication of x inverse b and x inverse, okay, that will be first you and do the transpose. So you do the b. Okay, you start from the b. Okay, what's on the b? LKKM. X inverse. We use x inverse to represent element in the x inverse. Okay, so BLKKM. That's the b times x inverse. Okay, and then k goes from 1 to n. Okay, and now this also times the another in the front, xml to lk. That's the multiplication of x inverse multiplied by b. Okay, and since we are looking for the trace which is diagonal matrix, so we let this m equal to this m. So we sum them out, that'll be a trace. And don't forget there's a negative right here, okay, in front. So this is the trace of this. Okay, you expand it out, it's gonna be this. Okay, now the BLK only be 1. Okay, when L is equal to I, K equal to J. So we did the L equal to I and K equal to J. L equal to I. So you have M, L equal to I, ML, X, ML, and then X K equal to J, XJM. Okay, and there is all zero, so we can remove this guy, the two summations, because they are all zeros except when the L equal to I and K equal to J. Okay, and this M remain. Okay, here. Okay, so if you look at this, the summation M. Okay, negative xi inverse x inverse xjm inverse. So you can move this, to the front. Okay, so it becomes negative summation negative x j m inverse times x mi inverse. And this summation m, this is the the ji's element in the product of x inverse multiplied by x inverse itself. Okay, and remember we define the numerator or layout. We have the partial x ij xij with respect to partial xij, not partial, sorry, partial the trace function. Okay, the function with respect to xij is actually the ji's element. Okay, so this is ji's element. Okay, so that's exactly mentioned our layout, numerator layout. So this is the now equal to the negative x inverse times x inverse. Okay, so that's a tricky part because the numerator layout, the element at the ij element is the ji element of this partial term. Okay, so it turned out that the result is negative x inverse times x inverse. So the result is quite neat. Okay, so that's all I have about this video. Thank you very much.